Hello, everyone. Welcome to the fourth talk of the Chromatic Seminar. So today, Rushil will talk about complex Buddhism. So, Rushil, please take it away.
All right. So, hello everyone. Thanks for coming. Um, so Last week, Amartya was telling us about Lazard's theorem and this sort of like algebraic machinery of formal groups. And in particular, we showed that for any sort of complex-oriented cohomology theory, which we've defined as a cohomology theory that has a certain like degeneration of the interior Herzberg spectral sequence, then we like sort of know the homology of classifying spaces of unitary groups. So in particular, we know the homology of like CB infinity. Um, and that's really useful because it tells us uh, that there's like a deep connection between complex-oriented cohomology theories and formal groups. But like as we know it so far, this connection is like very algebraic. Sort of like goes through this like Lazard ring. And the sort of meta goal of this talk is to sort of show how you can sort of recover this connection through a construction that's like much more geometric and like sort of internal to the world of stable homotopy theory. Um, to say something, maybe let's start with that intuition, and then I'll say some more about it as we go along. So to start with, section 1. So we want to define a spectrum that is universal among complex-oriented cohomology theories. This is going to be the spectrum of complex Bordism. So to do that, we're going to go on a short digression on like what it means for a cohomology theory to have like an orientation. So recall that if zeta is a rank n vector bundle on, maybe I'll write this as on some topological space X, and without loss of generality, it has a metric. For example, if X is paracompact, then we can define the twisted E-cohomology to be E star minus zeta X. And this will be the relative cohomology of the disk bundle to the sphere bundle. You recall that like these things, you get them by sort of like taking the unit disk and unit sphere at each of the fibers. So this is like basically writing down something that looks like a Tom space. I mean, it is a Tom space. So like as an example of this, if C is the rank n trivial bundle, so I guess that'd be Cn times X over X. Maybe you need this to be a real bundle. Then you know that the disk bundle is just the n disk times X, and the sphere bundle is just the n minus 1 sphere times X. And that implies, and this is like a consequence of the Thom isomorphism theorem, that this twisted homology is just the same thing as the degree n shift of the cohomology of X. And note that if E is multiplicative, then this twisted cohomology lands in EX modules. So with that out of the way, we can define what it means for a vector bundle to be oriented with respect to a certain cohomology theory. So here, zeta is a rank n vector bundle, and E is some multiplicative cohomology theory. So like i.e. like a ring spectrum. So then we can define an E orientation of zeta to be a class U in this twisted cohomology such that for every point x, then the restriction of U, which of course lands in En minus zeta x over x, which sort of by the above example is just the zeroth cohomology of the point. So like you think of this as being, like the sort of the ring of coefficients associated to your cohomology theory, or degree 0 of that. So for every point, then this element generates pi star E, as a pi star E module. More suggestively, you basically want this to be a unit, but like with some additional conditions. And then if this is the case, we say that U is a Tom class for zeta in E cohomology. And like, of course, this terminology comes from the sort of traditional Tom isomorphism theorem, which says that, like basically like every rank n vector bundle on your space has a Tom class, and it induces this kind of isomorphism that lets you just like shift degrees on cohomology. So, and like furthermore, like keep in mind that sort of this isomorphism is non-canonical, but like the only possible elements you can get are just going to be off by like a sign. So it's not actually that big of an issue. And sort of like as a consequence, and this is effectively the sort of same argument we had last time for the sort of like generalized Atiyah-Herzberg spectral sequence, is that this condition actually gives us an isomorphism between the cohomology of X and the twisted shifted by n cohomology of X, just given by multiplication by this Tom class. So then the goal is sort of twofold here. So one, we want to show that all complex-oriented cohomology theories have canonical E-orientation for every complex vector bundle. And like this canonicity will like include lots of other things, sort of like being like functorial and having nice like sort of properties with respect to like direct summed and pullbacks and whatnot. And sort of to do this, we want to show that there's a spectrum really a ring spectrum, which we're going to eventually define as mu, such that maps from mu to E, these are maps of ring spectra, classify E orientations. Or as in like they classify like choices of E orientations. And the point is that if you have a complex oriented cohomology theory, emphasis on the oriented there, like you've picked a choice of complex orientation that like this thing will sort of let you generate excuse me. Like this thing will basically let you sort of construct canonical orientations for like all your complex vector bundles. And then we want to see that that these ring spectrum maps sort of like classify complex orientations. And that means that that maps from this ring spectrum will sort of like give us all the data of these sort of like Tom classes. And that means that it'll like be able to know everything about complex oriented cohomology theories. And that's going to effectively connect us back to where we were with like formal groups and whatnot. Okay. So now,
I actually have a question. Do
yeah,
we
sure,
want
please.
to orient just complex bundles or stably complex bundles?
According to Lurie's notes, we want to like orient like complex bundles of like any given rank. So yeah, I believe it's the first one. Okay. So to prove one, sort of it suffices to consider the case for the classifying bundle over BUN. And this is well, this is just like a um, how do I want to do this? So what we know is that we have a fibration from S2n minus 1 to BU n minus 1 to BUN. And so like as a consequence of this, we can identify the sphere bundle of zeta BU n minus 1 and the disk bundle of zeta with BUN itself. So by what we've proved above, this tells us that the
Sorry, but shouldn't be the zeta the principal bundle with the fiber UN and not the vector bundle?
Just take the associated vector bundle.
Okay.
Yeah.
Okay, so your notation S of zeta means that you take the associated bundle and then. Okay.
Yeah. Like we definitely need zeta here to be like a vector bundle. But yes, that's a good point. So this gives us the following isomorphism, the canonical isomorphism of the twisted cohomology of BUN to the relative cohomology of BUN minus 1. So like, what is this? Well, we so like recall from Amartya's talk that the cohomology of BUN is going to be the power series ring E star on some generators C1 up to Cn. And the restriction map, so I'll write theta from E star BUN to E star BUN minus 1 is a surjection, and this sends Ci to Ci. And what that tells us is that sort of by like the standard long exact sequence, that this group over here is just the ideal generated by Cn in E star BUN. So maybe that's clear. So because this is like free over this group over here, then that implies that the class, Cn living in E2n of BUN minus 1 is a Tom class.
I'm sorry, once again, I have a slight problem. Is it the ring of power series or the ring of polynomials?
Ring of power series. So these here are like double brackets. So that's like power series.
Yeah, because I just don't understand how this works, because
Sure.
it seems that we should take invariant polynomials on the Lie algebra of the torus, and we'll get polynomials and not power series. And also, if you consider the spectral sequence of the principal bundle, you should have this ring annihilated by the exterior algebra. And this will only work if you consider polynomials, I guess, but I'm not sure.
Marcy, do you wanna jump in on this? Like it definitely should be power series. This is like a sort of conventional homotopy theory, is that
right, that's right. I mean, I kind of see what he's saying, but yeah, this is also kind of a subtle thing that I was thinking about.
yeah.
Yeah, it always trips me up. Should it be the polynomials or the power series?
Yeah, so right, so yeah, I would also actually we can have maybe a discussion about this after the talk, I guess.
Yeah.
It's
Okay.
worth having a chat. Okay. So yeah.
So
Good.
yeah. So what happens now is that this is the claim here. So then how do you see this? Well, we want to check that for every point x in BUN, that like our condition star up here holds. And because BUN is connected, we can just check it at one point. So so we can do is that we can take zeta, which is the universal bundle, or sorry, the vector bundle associated to the universal bundle on BUN, and then take its pullback by BU1 to the n. So we'll call this map F, and then And then Cn will get replaced by the image in this, which is just the ideal generated by T1 through Tn in pi star E T1 through Tn, which is just, if you remember, the cohomology of Bu1 to the n. So that means that Cn will actually get mapped to the product T1 W/Tn. And now by, I guess, the splitting principle, this pullback of this bundle is just the direct sum from 1 up to n of the individual pullbacks of the canonical bundle on Bu1, which is just Cp infinity. And then because of this, we know that we only really need to check what happens in the case n equals 1. And then we can sort of like bootstrap that up. So what happens over there? Well, then E star of Bu1 is just the same thing as the reduced cohomology of Cp infinity. And then for our class U to be living in Cp infinity, so this is an orientation of the universal line bundle if it maps to a unit in the reduced second homology of the S2, which is just, let me write this as pi 0 of E. And then, like, at this point, it's just sort of like trivial because sort of like by construction, U here just maps to 1, and then we're done. So this doesn't sort of like gives us everything we want in the universal case. So in general, we can write any vector bundle of rank n as the pullback of the universal bundle on BUN. So here, zeta prime is just going to be the pullback of zeta. And then we can define an orientation U of zeta prime in U2n minus zeta prime of x to just be the pullback of U, where this pullback will map from U2n minus zeta UN over to U2n minus zeta of x. So what this does is that in particular, you know, our system of Tom classes is natural, sort of by construction. Okay. So are there any questions so far? I'm running slightly behind on time, so I might try to speed things up a little bit. Okay. So, and now just to recall is that in the last talk, I believe we constructed Chern classes. You know what, maybe I won't say this. This isn't actually that important. So anyway, let's sort of get to the main definition here. So for every integer n, or maybe we need positive integer, whatever. So define MUN to be the Thom spectrum given by the desuspension of BUN of zeta n, where here zeta n is the universal bundle of rank n. And now, so to recall that if we restrict zeta n to BU n minus 1, we just get the sum of a trivial bundle with zeta n minus 1. And that implies that there's a canonical map from mu n minus 1, which is 2 minus 2 n bu n minus 1 zeta n minus 1. And this is just like by properties of Thom spaces that they sort of like turn, what I want to say, sums of vector bundles into suspensions, sums of trivial vector bundles into suspensions. So this is the same thing as bu n minus 1, 1 plus zeta n minus 1, which is, oh, look at that. That's just zeta n. And therefore, this thing maps to the negative 2n desuspension of bu to the n, zeta n, which is just mun. And then sort of note that the universal Thom class that we constructed this is the same thing as a map of spectra phi from mun to E. If you just like trace through the construction, like this will become kind of apparent. So, oh, and also like I should clarify some notation here is that like every time I write down something that's not technically a space, I mean it as like its suspension spectrum. This functor is like fully faithful, so like who cares? So in addition, the I guess like naturality of Chern classes implies that
sorry, in what sense the suspension spectrum functor is fully faithful?
Oh, sure. So what I mean to say is that when I write that like, oh, this thing, like a priori, this guy is just a space, and like this is a Thom space. But I really want to say the Thom spectrum, which means that when I write this, I really mean this. Where like this is the suspension spectrum.
Okay. I just didn't understand why it is fully faithful or faithful or.
Oh, why is like this functor fully faithful?
Yeah.
Oh wait, no, that's completely not true. Never mind. Sorry, my apologies. This functor is not fully faithful. But like we're doing stable homotopy theory, so like
yeah, sure.
So who cares? Like it's just you just do it. I'm not gonna write this out every time. Okay, but in any case, we this will actually give us a series of maps from mu0 to mu1 all the way up. Note that mu0 is just the sphere spectrum, and then I'm going to define mu to be the colimit over all of these guys. So yeah. And sort of aside, mu has a geometric interpretation as having its homotopy groups sort of being identified with the group of Bordism classes of n-dimensional manifolds with a stable, almost complex structure. If I recall correctly, I think this is what's called the Tom-Pochyagan theorem. Does anyone want to back me up on this?
Yeah, I think that's it.
Okay, cool, great. So that's nice.
Yeah, great.
All right. So now what we want to do is show that how do I want to do this? Yeah, so now what we want to do is show that so let E be complex-oriented homology theory.
Yeah, actually, I wanted to note that the previous result can be expanded, that if you evaluate the thing on arbitrary space, then you get Bordisms like over this space. So
yeah,
manifolds are kept with a map to this space.
Yep, exactly. That's true. Yeah, thanks. So okay, so basically the goal is we want to say that E infinity ring maps mu to E, or I shouldn't say E infinity, ring maps mu to E are the same as complex orientations of E. So like, yeah. So to sort of start, we need to first figure out, what is the ring structure on mu? So so to see this, what we use is the fact that there's a map that goes like this, where this takes this classifies direct sum of vector bundles. So then by taking Tom spectra, we get a map from MUA tensor MUB to mu a plus b. And now, sort of like importantly, because of what we've identified as the sort of inclusion maps here, we know that the map mu n minus 1 to mu n, this is the same as the map mu n minus 1, which is just the sphere times mu n minus 1, which is just mu0 times mu n minus 1. And then we can map this to mu1 times mu n minus 1, where here this map mu0 is just the sphere spectrum, and mu1 is well, it's the d-suspension of Cp infinity, and this map is just the unit. Sorry. So this is just the map that's classifying the complex orientation. And then the multiplication on mu, all this MAB. So here we have M1 n minus 1. This gives us a map to MUN. And then this is compatible. This is exactly the same map that we previously defined. So what that means is that taking the colimit, mu has a multiplication of mu tensor mu to mu. And fact, mu is actually an E infinity ring spectrum, which is pretty helpful. So now just to recall that for E, some complex-oriented cohomology theory, we know that for every integer n, we get canonical orientations Cn of the universal rank n vector bundle.
I have a somewhat of a stupid question. Isn't it strictly commutative? I mean, sure, it is an infinity ring, but do we really need that?
I mean, like, to me, commutative and E infinity mean the same thing.
Okay.
But like, maybe that's a bizarre statement to make. Like, okay, sure. The point is that like, it's commutative up to homotopy. Like, it's not literally commutative, and that's because like if you like try to I guess commute direct sum of vector bundles, then these things aren't like literally equivalent. They're like isomorphic. That's kind of what's going on. But the point is that like all of the
but they're like isomorphic. They're not. We don't need to perform any sort of homotopy to get from like one image of Seagram up to another.
Yeah, but they're not like.
That's my point. That it's well, it's strictly commutative. But maybe there is an example that I don't understand. I just have this picture with like Seagram up for Cp infinity, and maybe in higher degrees it's not like that.
I'm not entirely sure. Yeah, I don't. I'm very sure of the fact that like MU is not like strictly commutative. I'm just not sure what a really clear way to see it is, other than saying that like strictly commutative things are just like weird objects. Yeah. All right. Maybe I'll address that a bit later towards the end. But I'm not super sure I can tell you all the details. Like the point being is that like in general these sort of like E infinity ring structures are like it takes some work to like show that they are what you expect. Okay. But I'm running pretty low on time, so I'm just going to try to say the useful things. So we know that any complex orientation of zeta n is equivalent by definition, or sort of by construction, to a map from mu n into E. And these satisfy the following conditions. First is that the map from mu1 into E, classifying the canonical orientation of the universal line bundle, is just the complex orientation. And two, these maps are multiplicative in the sense that the following diagram commutes up to homotopy. So that's great. And three, it's even true that if you look at the composite map from mun to mun plus 1 to E, this is Vn plus 1. If you take this composite, then you actually get back phi to the n. And all that implies is that so 1 phi here. So we get a map phi from the colimit of mu to E, basically by this third condition. And this is a map of ring spectrum. Because it preserves the multiplication of the unit. So yeah. And in fact, so if we look at the inclusion of mu1 into mu, then because this thing is just a desuspension of Cp infinity, this is the same thing as a class in the reduced second homology of Cp infinity. So we call this class T, then T is the sort of canonical orientation of mu. And in fact, because of our condition 1 up here, our map phi as we've defined it sends T to the complex orientation of E. So What does that mean? It means that we have this bijection between maps of ring spectra and orientations of E given by sending some map phi to its image of this class here, and by sending some class here to the unique map phi prime such that phi prime of T is equal to T prime. And this is a bijection. So the sort of concise way to state this is that mu is the universal complex-oriented cohomology theory. So like this is basically like the main fact I want you to like take out of this. And then in the last 5 minutes, I'm just going to say briefly that, this is all very well and good, but the thing we really want is to connect mu back to formal groups and Lazard's theorem, because if this is the universal complex-oriented cohomology theory, it should be like, in some sense, like the universal, associated with like the universal formal group law. It turns out that like this is true. So there's a theorem due to Quillen that the map L to mu star, this being given, of course, by the sort of canonical formal group arising on mu from the universal complex orientation. So this map is an isomorphism. And in particular, it's an isomorphism of it's an isomorphism and it respects the universal formal group. Well, so what this says, and this is like slightly stronger than just like some sort of computation. Okay, so like let me sort of step back for a second. It turns out that the homology of mu is like really easy to compute. I'm going to like do it in like the next like 2 minutes. The homotopy groups of mu are like much harder. This is like requires like the sort of machinery of the atom spectral sequence. This is like the subject of Grigory's talk next week. But the actual computation of like the homotopy groups of mu of like computing what this is actually due to Milner. And like that's not like this like the really hard part. The hard part is showing that like the formal group law or the universal formal group law, like it's showing that this isomorphism or this map, which sort of comes from sending the universal formal group law on the Lazard ring to the formal group law on mu star, like is an isomorphism to the effect that the formal group law on mu star is the universal formal group law. Like this theorem is an identification of like objects that sort of represent the moduli space of formal groups. So it's like much stronger. Okay, but anyway, I should sort of like hurry up and say the useful thing right now. So well actually let me just say it. So additionally, by like just some algebra, there's like nothing like very, very deep or anything. You can prove the following proposition, which is that if E is a complex-oriented cohomology theory and you have some elements Bi in the homology of two-shifted CP infinity, which are dual to the basis ti plus 1 of the ideal generated by t inside pi star e of t. So you think of this as like the closed point in the scheme. Then images of bi in e star of mu determine a ring iso from pi star e for polynomials on all these generators with e star of mu. And like all this really going on here is that you sort of look at the how do I want to say this? So you can identify the magic sauce here is that you can identify the homology of e star of mu n with the n symmetric power of the e star homology of bu1, and like we know what this is, so from there it's just like it's like not very fun. So what does this tell you? It says that as a sort of direct consequence, the integral cohomology of mu, or sorry, the integral homology of mu is just a polynomial ring on infinitely many generators. Yeah. Okay. So that's basically where I'm going to stop. And then next week, Grigory will talk about the spectral sequence and like how you can use like sort of this fact and the spectral sequence to sort of like compute the homotopy groups of mu and then effectively like prove Bowen's theorem. Okay. So are there any questions?
Okay, so first let's thank Rushil again.
All right.
Okay, so I guess I can stop the recording and we can talk about a few things. Thanks.